Okay. So I backtracked just a little bit so we can go back over epoxidation. Okay. So remember that we form epoxides by reaction of an alkene with a perbenzoic acid or peroxy acid. So it could be anything that has this structure in it. The identity of the rest of the molecule can vary. You could have a methyl group in the place of this benzene ring and it would still work. The feature that you need to have is the uh, what's called a peroxy acid. So it's a carboxylic acid, but notice the peroxide bond here. So you have to have this in order to create the epoxide. And then we talked about how epoxidation is a syn addition. So if you do the reaction with MCPBA on a ring, you do need to indicate stereochemistry and you need to show that it is a cis product. So remember, syn addition means that it happens on one face of the double bond. We looked at the like stereochemical outcomes of cis versus trans alkenes. So if you end up, if you start off with a trans alkene, your product is going to maintain that kind of trans appearance. So remember, you know, if it's not necessarily trans, but maybe like E or Z, you still have to keep those groups in the same relative position to each other. So these methyl groups are going opposite of each other right now. So in your product, the methyl groups should be opposite of each other. If you had other things coming off of here, they would need to be in the same relative positions. If you're starting off with a cis alkene and it's symmetrical, you'll end up with only one product and it will be meso. In all other situations, you would end up with an enantiomer. So if it was cis and asymmetrical, you'd have a pair of enantiomers. If it's trans, you're going to have a pair of enantiomers as well. When you do reactions with epoxides, these reactions are really interesting and they can let you create some really cool compounds. So this is something that we're going to use pretty often. Epoxides are under a ton of ring strain because they're a three-membered ring, which makes them highly reactive. So if you introduce an epoxide to essentially anything, it's going to be opened and it will happen very quickly and easily. So if you leave an epoxide out on like a wet day, like a humid day, it's going to react with the water in the air. And then depending on the conditions, whether it's acid or base catalyzed, you end up with a different outcome. So if it is acid catalyzed, remember the nucleophile is going to attack the most substituted carbon. If it's base catalyzed, the nucleophile will attack the least substituted carbon, just like you would expect of any nucleophile. One of the things that students trip up on a lot when it comes to the mechanism of this is in the acid catalyzed ring opening, you're going to protonate the oxygen before you start the rest of the reaction, which makes sense because you're an acid. The first step should be that you protonate something. And then you'll have to most likely deprotonate where your nucleophile was. So in this case, our nucleophile was water. We ended up with an extra proton here. So our first step was a protonation. Our last step was a deprotonation. In a base catalyzed ring opening, you're not going to have that initial protonation step. The only trick to this is that when you open up the ring, you're going to end up with an alkoxide, and you will end up having to protonate that to get the alcohol. So the last thing that we talked about was the regioselectivity with the asymmetric epoxides. And again, I'm just going to repeat what I said a second ago. The nucleophile attacks the least hindered, least substituted carbon. So this is just a normal nucleophilic situation, like an SN2 reaction. In an SN2 reaction, a nucleophile is going to prefer the less substituted substrate. In acid, the nucleophile will attack the most hindered carbon. Okay, and then we already did this question, so we're gonna move to this one. Okay, This is the problem that I gave to you guys at the end of class and asked you to think about it. Did anybody work on this mechanism? Okay, that's okay. How about this? I'm going to put you into breakout rooms for about 2 minutes to think about this. And while you're in the breakout room, I'll also look up the final exam schedule. I want to clarify what this means. So the carbon that has a star on it is the same carbon atom. So it's been labeled with carbon 14. This is actually a really common approach to figuring out the mechanism of a reaction to kind of track where the carbon 14 atom ends up in the molecule. So in this case, the carbon 14 atom is this atom right here, and it's in the epoxide. But then after a reaction with ethoxide, the carbon 14 atom is here attached to the ethoxide. So the carbon framework is not changing, but the location of the epoxide is. So you can label the 3 carbons this way as well, A, B, C. So we are not changing the location of the carbons. So what I want you to do is think about what is the mechanism of this reaction. I want you to draw it out stepwise and see if you can figure out how this ends up happening. My hint here is that it is not directly ethoxide attacking carbon A and kicking out chlorine. If it were, the ethoxide would be over here and the epoxide would not have seemingly changed locations. So it's not that simple. Are there any questions about what I want you to do? Okay, I'm going to put you in breakout rooms. While I'm putting you into breakout rooms, I'd like to point out I do look at who is actually speaking in the breakout rooms, who is participating. And when you don't go to your breakout room, when I assign it to you, I take note of that as well. So there's a handful of you who are kind of on that list. I know that we're coming to the end of the semester, but today we're going to do a review session, and I am going to put you into breakout rooms. On Wednesday, we're going to do reviews, and I'm going to put you into breakout rooms. If you're not going and you're not participating, you're really not getting anything out of that. And I put you guys into breakout rooms, not because it's a fun waste of time during class, but because I think it's really valuable for you to talk to your peers and use, OCHEM terminology out loud and think through a problem together. So please make sure that you're going and that you're participating. I'm doing this because it is scientifically proven to be a successful way of learning. So I'm assigning you guys to your groups now. Please go and work together. I forgot to resume recording. Sorry about that. Okay, I'm going to minimize this and move on to the question. Okay, I'm going to give you a pretty good amount of time to work on this. Okay, about 30 seconds to finish up. Okay, so can't see what you guys voted for. Okay. So kind of mixed results. Some votes for one, a lot of votes for two, almost no votes for three, and a lot of votes for a mixture of one and two. Okay, so let's figure this out. So what's going to happen initially?
You protonate the OH group.
Sorry, did you say protonate or deprotonate?
Deprotonate.
Okay. So we have hydroxide. We're going to deprotonate the alcohol. And that gives us I'm just going to draw out the ethyl group for time's sake. Okay. And then what happens next?
Got to get rid of the bromide.
Right. So what happens exactly?
The oxygen attacks the carbon, which then
Right.
kicks out the bromine.
Right. And what do we know about the stereochemistry of this? What do we usually call this type of attack?
Backside?
Right. This is a backside attack. This is an SN2 type attack. Okay, so we know that we're going to form an epoxide. That's what most of the votes were for, which is correct. How do we pick between 1 and 2?
The stereochemistry.
Right. So I guess I have to tell you which one's correct. So number 2 is what would happen, but why?
Whenever you do a backside attack, it flips the stereochemistry that's already present.
Right. So it's an inversion of the relative configuration. So the oxygen is coming here and attacking from the back, pushing out bromine. When that happens, the methyl group and the hydrogen are going to get pushed down. So the methyl group is going to stay on a wedge. The hydrogen is going to stay on a dash, but they're going to end up getting pushed down. And that's how we end up creating number 2. Does that make sense? And I also want to point out that in this case, it went from RR to RS. So it was a literal inversion of stereochemistry. But remember that depending on the identity of your nucleophile and your leaving group, when you do an SN2 reaction, it may not change the actual, official designation of the chiral center, but it changes the relative configuration, which might not be different from the absolute configuration. Okay, so that's how we get question number 2, or answer number 2. Sorry, I resized the screen a couple times so I could see the image. Okay, so that's it for top hat today. So if you want to close down top hat, you can. Okay, so this brings us to our last, I think, 3 slides of chapter 11 and of OCHEM 1 lecture. So we're almost done with new material. Everything from here on out after these 3 slides will just be review. So the other 2 methods that we know for creating vicinal diols result in the formation of a cis diol. So we learned that you can take an alkene, and there was the route that had potassium permanganate and several other reagents, and a route that had osmium tetroxide and several other reagents. I'm not writing out the whole thing just because there's not a lot of space. And both of these gave you a cis vicinal diol or glycol. This route is going to give us a trans diol. So using MCPBA, we make an epoxide, and then you can react in acid or in base. Remember, this is going to affect the regiochemistry only of your outcome. But in either of these situations, you would bust open the epoxide and create a vicinal diol. The difference being that this is going to be trans. So this is the exact same situation as when you take an alkene and react with a halogen at room temperature. You end up going through a 3-membered bromonium ion, which is then attacked by bromide. Giving you an enantiomeric pair of trans dibromides. This is the exact same mechanism, exact same outcome. So we are using MCPBA to create a 3-membered ring with oxygen as the central atom. And then we are attacking with a nucleophile to break it open to get the trans outcome. Does that make sense? If it doesn't make sense, do we have a question?
What specifically is?
Sorry, can you say it again? I think you cut out.
I'm good.
Okay. Cool. So again, if there was another substitution on one of these carbons, that would actually limit your outcomes based on whether you were an acid or base. You could end up with only 1 molecule. So just keep that in mind. So our next thing is the formation of what's called a polyether from an epoxide. So this is another type of polymerization. The other polymerizations that we've looked at are radical based. When you get to OCHEM 2, you'll learn yet another type of polymerization. But this one would be initiated by reacting an excess of epoxide. So there would be a lot of this in our reaction mixture and a small amount of an initiating nucleophile. So the nucleophile attacks the epoxide. You break open the epoxide ring. This is carbon A, this is carbon B, carbon A, carbon B. Now you have an alkoxide, which just continues the reaction. You keep adding on ethers until you run out of epoxide material, basically. And then when the reaction has stopped and you're at this point, you would add in some source of protons, probably like something really mild that wouldn't cleave any of these bonds. So like methanol would allow you to protonate that last bit there. This is the type of question that's like really difficult to test over. There's not really a good way to test over this. This is kind of more of a fun fact slide, I guess. Are there any questions about polyethers? Okay. So then our last topic is one that's actually really important to me and like what I did in grad school. So this compound here is called a crown ether. So it's a repeating ether, but it's cyclic. That makes it a member of the cycle class, essentially. So it's a cyclic molecule that's quite large, and it's a cyclic oligomer of ethylene glycol. Oligomer is a term that means it's kind of a polymer, but doesn't have as many units as a polymer. It has a defined number of units. The way that crown ethers are named is they're called X crown Y. So X is the total number of carbon atoms, Y is the total number of oxygen atoms. So what would be the name of this compound here?
Would it be 12 crown 6?
Yes. So that's something that I often put on a test. Hold on. This is not. Sorry, I said it and then I was like, that does not make sense to me. It's the total number of atoms because this would be 18 crown 6. Sorry, I knew the name, I had it in my head, and then you said 12 crown 6, and I was like, that's what the slide says, but that's not correct. It's the total number of atoms, period.
Okay, so oxygen and carbon.
Yes, so you would add up all the atoms that are in the cyclic arrangement, not including the hydrogens, because they're not part of the cyclic arrangement. So, okay, total number of, oops, that was meant to be a C, that was bad. Carbon and oxygen atoms. I apologize, just cross that part out in your notes. Okay. So 18 crown 6 would be the name of this one. I do put this on your test. I think it's a nice little freebie. I tend to give you a multiple choice option. So if you know that it's the total number of carbon and oxygen atoms and then total number of oxygen atoms, you can come up with that answer very easily. So 18 crown 6. Now, the reason that these are important and near and dear to me is that crown ethers were one of the first macrocycles really discovered and studied. And macrocycles are well known because they can have what's called a host-guest relationship. So a host-guest relationship means that you have something that's larger and something smaller can fit inside. So you have a host molecule, such as the crown ether, and you have a guest molecule, such as a potassium ion. Now, these are really useful because you can solubilize salts in nonpolar solvents. The reason that this would matter is that if you were attempting to do a reaction in a nonpolar solvent and you need to isolate the fluoride ion, potassium fluoride is not going to be soluble in a nonpolar solvent. But if you introduce a crown ether, you can actually solubilize the salt and free the anion, which would mean that you could, do a reaction using that anion. So you can actually improve an SN2 reaction by isolating the nucleophile. This is very similar to when we looked at solvent effects. And crown ethers specifically can act as what's called a phase transfer catalyst, which means they can bring ions into nonpolar solvents. So if you were doing a reaction in a beaker, and say you had 2 layers in your beaker, your top layer would be organic. Most organic solvents are less dense than water. Well, not most, but some are. And your organic layer might have, say, an alkyl halide or something that's not soluble in water. And in water, you have a salt. Now you introduce the crown ether and you stir or shake your reaction mixture. Your crown ether can help pull ions from water into your organic layer. It's not going to cause your layers to mix necessarily, but it will help you move what you need from the water layer to the organic layer. So this is why it's called a phase transfer catalyst. It can bring something from aqueous to organic. Now, the reason, again, that this is important to me is that my research in grad school was all in macrocycles. Specifically, my research field was called supramolecular chemistry. So I synthesized very large macrocycles that were made from larger repeating units and studied the host-guest interactions and the other things that they could do. One of the really cool features of the molecules that I worked with was that they were really good at solubilizing mostly like cancer drugs. So most drugs that are discovered that have activity against cancer are actually not soluble in water, which is really unfortunate because the human body is mainly water. And if you need to get that inside the human body, you need to get it to a tumor, it needs to be able to be solubilized. And so that was a lot of the work that I worked on, was creating containers that could solubilize those drugs. And then we worked on adding things to those containers that could help the container actually focus on a tumor. So it could actually target like a receptor in the tumor. But anyway, so the crown ethers opened up a really large field, which is still very actively studied and researched. So anyway, if you are taking your test, don't be surprised if you see something about naming a crown ether. It won't be 18 crown 6, it'll be something else. I also sometimes ask about the effect of adding a crown ether to a reaction. And that is the last slide of this chapter. Cool. So how do you guys feel being done with the last bit of material?
Good.
Yeah. I'm really impressed that we're done. That's literally never happened. I'm usually rushing through chapter 11 and possibly chapter 10, trying to get all the information into my students' brains. Cool. So from here, we're going to switch to review mode. So I actually shared the review with you guys last night by email, and the file is up on Canvas. So the first thing that I did was I kind of wrote a list of the main topics in every chapter. This is not a complete list by any means. I just kind of highlighted the main points. You do need to go back through, and if you're looking at this list and you're like, I don't remember anything about inversion of stereochemistry, you need to go look that up. Or I don't remember how to name alkenes, cis, trans, or E and Z. You need to go look that up. So that's kind of the main point of this list. And then here I listed out the different reactions that you learned and some of the key features about them. Chapter 9, it's NMR, so I just suggest that you go back to the PowerPoint. I think that's the best way to go review that, is to look at the images. Chapter 10 summarized, and then chapter 11. And then just a whole ton of questions. So did anybody happen to look at this already? And do you have any specific questions you would like to go over? I just got a question in the chat. The final is comprehensive. It'll go from chapter 1 to 11. The second part of the question is, does it lean more towards material from exam 2? I would say it's pretty even, but if there's any topic that you see a lot more of, it's probably going to be substitution and elimination. But there will be questions on every chapter. So you will have early nomenclature like of alkanes. There will be Newman projections. There will be acid-base chemistry, stereochemistry. The final exam is definitely comprehensive. Exam 2 will be limited to what you see in this list. So again, did anybody look at this and have a specific question they wanted to start on? If not, we'll just start at the top. Okay, cool. So the first question says, provide the structure of 3R, 4S, 3-bromo, 3,4-dimethylheptane. I'm gonna make this a little bigger. Okay, so this is actually something that we don't do that often, which is drawing the structure of something with stereochemistry. Now, you're not going to have to draw any structures for your exams. There's not really a way to submit that type of question. But if you are asked which one is 3R, 4S, 3-bromo, 3,4-dimethylheptane out of a multiple choice list, usually the best way to approach something like this is to go ahead and draw the correct answer first and then look for it. So let's start with like from the ground up here. So it's going to be a heptane. So how many carbons are there going to be?
6.
Mm-hmm.
7, sorry.
Okay. I think I said, I just assumed you were correct and started drawing 7 carbons. Sorry. I'll be more attentive. Okay, so then 3-bromo, 3,4-dimethyl. So carbon 3 and carbon 4 are going to have methyl groups. Carbon 3 is also, oops, oh, come on. Carbon 3 is also going to have a bromine. So when I go to add stereochemistry to a structure like this, I first assume that my lowest priority is already facing backwards, and I determine what the stereochemistry is in that position. Excuse me. So what would be the high priority on carbon number 3?
The bromine?
Right. And then between the ethyl group and the entire rest of the molecule, what is the next priority?
The whole
The
rest of the molecule.
Right. Stop. Sorry.
How does it do that?
It's from my hand hitting the screen. It decides to open up the typing. Okay, so 1, 2, 3. If 4 was already going to the back, what would be the stereochemistry of this molecule?
It'd be S.
Right, so it'd be 1, 2, 3. That would be rotating to the left. That would be S. So if we want R, then we need to put, stop it. Oh my gosh. We need to put our methyl group coming forward instead and put our bromine going to the back. That would give us the correct stereochemistry. So that's how I usually do it. I just assume that the lowest group is going to the back, and I check if it has the stereochemistry that I want. And if it's the opposite, I bring my lowest priority forward. So we need to do the same thing to this carbon. I'm gonna go ahead and draw the methyl and hydrogen out separately. So this would be 4. And then would the left portion or the right portion be our next high priority?
Be
Or
the
our
left.
highest? Yeah, it'd be the left side would be the highest, the right side would be next, and then the methyl group. So if 4 was going to the back, what would this stereochemistry be?
It'd be S.
Right, and is that what we want?
Yes.
Yes. So I'm going to replace this with dashes and then make this a methyl group coming forward. So that would be the correct answer. Does that make sense how we came up with the dashes and wedges?
Yeah.
Okay. And the other thing you could do is draw it and test it. But I think it's easier this way. Okay, so the next one says, provide the major product for the following reaction and the mechanism of formation of that product. So we have an alkyl halide. Is it primary, secondary, tertiary?
Primary.
Primary. So what are we already kind of limited to?
E2.
Yeah, SN2 is kind of the leading one here. It could also be E2, but we would need to look at the identity of our nucleophile or base. What do we know about sodium cyanide? Remember, this is sodium plus and cyanide minus.
A good nucleophile.
Right, cyanide is a good nucleophile. Is it a good base?
Not really. No.
Right. Yeah, it's not a good base. So it's not going to do E2. It's only going to do SN2. Also, remember when you're looking at your nucleophile, please cross out the counter ion. You do not need it. Since this will be multiple choice, I will include answers like this. If you pick them, I know that you are not paying attention. You're never going to put that counter ion in your product. Okay, what is the IUPAC name of the compound below? What is the
1-chloro-3-methylbutane.
Nice. Yeah, so you need to look for the longest carbon chain. It's 4 carbons. And then you need to decide if you're going to number from the left or the right. You want to number from the right because the chlorine is there. And that's how you end up with 1-chloro-3-methyl. Another thing that I sometimes do for the multiple choice is, so sorry, is maybe if I put it down lower, I won't have to rest my hand. I'll sometimes write out 3-methyl 1-chlorobutane so that you have the right numbers, but the alphabetizing is incorrect. So that's one type of multiple choice you might see from me. Okay, what type of reaction is this compound most likely to participate in?
SN2.
Yeah, it's really unfortunate that I put it right under this problem. I didn't mean to do that because it's very similar. This was from a quiz where I was trying to be helpful and give people some points, which is why the ridiculous answers exist. So, true or false, a reagent must possess a negative charge to act as a nucleophile.
True.
So what I would do is think about things that you've seen act as nucleophiles. We've used, so I hate this, I'm so sorry. I will not scroll down as much. We've used, we've used water, we've used methanol, we've used hydroxide, we've used methoxide. We have used things that do not have a negative charge as a nucleophile. So is this reagent, or is this statement true?
No.
Right. So it is false. You do not have to have a negative charge to act as a nucleophile. There has to be an excess of electrons and a good enough electrophile. True or false? SN2 reactions result in the inversion of stereochemistry at the electrophilic carbon.
True.
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 Right, remember this is called a Walden inversion. So I'm giving you the name in case you're like, I do not remember that and I need something to review. You can look up Walden inversion. The important reaction intermediate that the SN1 mechanism must go through is?
Carbocation.
Right, we go through a carbocation. What other mechanism goes through a carbocation?
E1.
Right, so E1 also goes through a carbocation. You can also include dehydration, which is also a type of E1 mechanism. And then also remember that addition to alkenes, the acid catalyzed ones tend to go through a carbocation. So adding like HX or acid catalyzed hydration, just listing out other things that go through carbocations. Okay, the correct IUPAC name for the compound below is, what is the longest carbon chain that we see?
6.
6. So I didn't do it in this one. All of these have hex in them, but sometimes you can eliminate options just by identifying the longest carbon chain. And then do we number from the left or the right?
From the right.
From the right. So you could already go through and you have this 3-chloro-4-methyl thing. Go ahead and get rid of anything that doesn't say 3-chloro and 4-methyl. So we have 4-chloro-3-methyl. That's not right. 3-methyl-4-chloro. That's also not right. 3-methyl-4-chloro. 3-chloro-4-methyl. So I only gave one option that had the correct numbering scheme. There is this option here as well. I probably meant to put the numbers correct on this one because it says 1-hydroxy. Make sure that you know that since this is an alcohol, it has to end in OL. So that's how you were meant to pick from this. I'm pretty sure I meant for this to say 4-methyl-3-chloro. That's the only way that works with that numbering. So D is correct. What do the letters SN2 stand for? Do you guys remember?
Bimolecular nucleophilic substitution.
Right. So that's not a question I would ask really. It's more just, you should know what that stands for because I do ask questions about the rate law sometimes. And remembering that it's bimolecular can help with the rate law. Okay, so given the reaction below, which reaction mechanism is most likely to occur? So we have a primary alkyl halide. So which ones can we already eliminate as options here?
SN1 and E1.
Yeah, definitely not going to happen. Okay, so then to decide between SN2 and E2, what do we need to look at?
The what it's gonna react with.
Right, so methoxide, does that help us decide between SN2 and E2 necessarily? Is it a good nucleophile?
Yes.
Yeah. Is it a strong base?
No.
No, it is a strong base. Okay, so this could do SN2 and possibly E2. What other factor can sometimes force elimination?
Bulky or small?
Yeah, if it were bulkier, that could favor elimination. It's small though, so it's less likely to favor elimination. What else is missing from here that could favor elimination?
Heat.
Heat, right? So no heat. Because of those things, I would say your major product is probably the SN2 product. In the box for number 8, supply the product of the reaction. Sorry, this was originally number 8. I copied and pasted a lot of this from old quizzes because you guys didn't get those quizzes, which means you've never seen these problems. So the way that we got there was we had just a direct displacement of bromine. The most common mistake for this type of problem is students drawing out stuff like this. And since you guys will not be drawing out your own products, I'm going to put common mistakes as possible answer choices. So if I were you, while you're taking your exam, I do allow you to have blank paper because I think you need it for this. Go ahead and draw out the reaction and the mechanism. Make sure that you know what you're looking for. So if you're looking at a list of 4 or 5 products that could be possible, don't look at those. Draw your own reaction, draw your own product, and then find your product from the list. That'll help keep you from picking one of these like traps here. Draw the mechanism, we already did that. Okay, for the reactions below, provide the major product. There's several of them here. We're gonna do them one by one. Okay, so did we get anything for the first one?
You protonate the OH group,
Right.
which prompts it to leave, leaving you with a carbocation, which then double bonds back to the benzene ring? Not benzene ring, hexane ring? Cyclohexane? Whatever it's called.
Okay, hold up real fast. So we have a secondary carbocation. Is this the best one we can make?
No.
No, where else could we put it?
The ring.
Okay, so now we can talk about the products. So what are our options here? So we are going to form a double bond. This turns into an elimination, right? This is a dehydration. Beta hydrogens.
Sorry, could you repeat that? You cut up a little bit.
Where are the beta hydrogens?
Could it be the carbon below it?
Mm-hmm. Where else?
It could be on the left side of it too, the very top.
Right. These two would be the same technically. So yeah, they are there, but they're going to lead to the same products. I just want to keep that in mind. Is there another type?
On the ethyl,
Right. Thank you for using the right term. I appreciate that. Okay, so if we pull off the one on the ring, that would give us one type of product. And if we pull off the ethyl group hydrogen, that gives us that product. We'll draw out the mechanism for one of them. Which one of these is better?
the one with the double bond on the ring.
Maybe. I actually think they're pretty equivalent. The one with the double bond on the ring might actually cause a little more strain on the ring, but they both have 1, 2, 3, three substituents. So they're fairly equivalent. The reason that I wanted to draw these both out and point out the potential carbocation rearrangement is that you would end up with a mix of these, I believe.
But
the double bond actually in the ring might actually cause a little more strain on the ring. So this one could possibly be the major one.
So yeah, that would be major. The other one would be minor. Yeah.
Yeah, I think probably they'd be pretty equivalent though, because there are more of these protons available. So sometimes number of protons can outdo that. Okay, next one. We have a secondary alkyl halide and we have sodium ethoxide in heat. What are we making? Or what's our mechanism going to be?
Is it going to be like E1?
Not E1 because you have ethoxide, which is a really strong base, but it is going to be
E2.
elimination, right? So our ethoxide, remember, we're not going to use sodium, just pretend it's not there. Our ethoxide is going to kick out the bromide. In the next one, we have potassium cyanide. What's going to happen in this one?
SN2.
Right. So we have cyanide, which is a good nucleophile. Can kick out the bromide. Oops, I forgot to ask you guys about the stereochemistry. I just went and did it. And make sure that you draw the inversion of stereochemistry.
wait, sorry, on that last question with the ethoxide and ethanol, does ethanol just not do anything?
It's the solvent. So The way that ethoxide would be created is actually you mix ethanol and sodium metal, and you end up with a redox reaction that creates sodium ethoxide and hydrogen gas. So you
Okay,
need,
thank you.
yeah, so you end up evolving off hydrogen gas, you end up with sodium ethoxide and a whole lot of ethanol left over. So it's usually a solution. Okay, next one, we have sodium hydroxide and a primary alkyl halide.
Does the OH group attack the carbon connected to the iodine, kicking it out?
Yeah, since this is primary, even though, oops, oh man. Even though hydroxide is a strong base, this is a primary alkyl halide. So you're much more likely to do a substitution, especially since there's no heat present. Okay, I think we should skip down. I got a bunch of good practice problems. We should skip down and talk about some NMR stuff for a little bit, because there will be questions like this. So for this question, you're not actually shown the structure. You have to draw it yourself. So for 2,3-dimethylpentane, this is our structure. How many unique signals would you expect in the proton NMR spectrum of 2,3-dimethylpentane? I'm going to give you about a minute to try and figure this out on your own. Okay, how many signals would we expect in the proton NMR? In order to answer this, I think the first thing you should do is draw out your different types of protons. So we have a methyl group here, so there's 3 protons here. We have another methyl group, which is identical to the other one, so those are not going to be unique. We have 1 hydrogen here, 1 here, 3 here, 2 here, and 3 here. So how many unique hydrogen signals is that?
Six?
Mm-hmm. And then go and draw this again. How many unique carbons are there? Oops. Sorry. So, I mean, another way you can do this is, draw out every carbon atom and then try and figure out if you have any repeaters. Are there any carbon atoms that are repeats?
The 2 groups at the very left.
Right, these 2 methyls are identical to each other. So we do not need to count both of those carbons. So how many unique carbons do we have?
6?
Again,
Right. Okay. So use the following structure to answer the next 3 questions. Identify the group of protons that is most de-shielded by drawing them in and circling them. This might be one that's easier to do on your own. I am going to send out a key, by the way, at the end of the day. Oh, let's do this. So I actually gave some spectra here for you to practice with. So the questions, you're given the molecular formula C9H10O. It asks a question about the IR peak, asking what it's most indicative of, how many unique carbons are there, asking you about, what do these protons represent? How many neighboring protons are there? Basically, a bunch of leading questions to help you decide between these 4 structures. Do you guys want to work through this together, or would you rather work through this one on your own? I can give you some more practice spectra also if you'd like.
Either
I
way.
would-
I think on our own and then end up working together.
Okay, well, we only have 7 minutes, so we're either going to work through this together right now, or you're going to have to work through it later.
We can work it together if you're going to give us more practice to do on our own.
Okay, yeah, I'll give you more practice problems then. They just won't have leading questions like this. So the first one says the IR peak at 1715 is most indicative of, let's look at that. So we're talking about this right here. What does this represent to us?
That's a carbonyl.
Right. So our answer is D. Let's look at our options real fast. Which options does that eliminate?
The first one and this.
Right. Neither of these have a carbonyl, so they are not valid answers. Based on the carbon-13 NMR spectrum, how many unique carbons are present in this molecule? So how many do we have?
7.
7 unique carbons. Are there any that are special here? Like any that really give us a good hint?
The proton decoupled on the left.
Yeah, so proton decoupled is just describing the type of spectrum, but yes, this one is special. It tells us about a carbonyl, right? So that confirms that for us. So we need to go up here. We have 7 unique carbons. Does that help us narrow down between these by chance? How many unique carbons are in the first structure here?
Is there 6 there?
Let's see. We have
7.
1 for the methyl, 2 for the carbonyl, 3 for the methylene carbon, 4 for this one, 5.
There, yeah, it's the same across,
Right.
except for the last one.
2, 3, 4, 4, 5, 5, 6, 7. All right, so that doesn't help us. The next question says, in the proton NMR spectrum, there are 5 protons represented in the cluster between 7 and 7.5 ppm. What do these protons most likely represent? So you shouldn't necessarily have to look at that given the range, but what would these protons represent? It says 5.
5 identical.
Are they identical?
Is that like the ring?
Right. This is indicating the aromatic protons to us. So it says that there are 5 aromatic protons. Does that help us choose between the 2 structures?
No. No.
Well, we can check.
So it's the one without the methyl.
Right. It has to be this one because it has 5 aromatic protons, but we're going to continue to confirm that. So how many neighboring protons does the set of 2 at 3.6 ppm have? So does how many neighbors do these protons have?
1.
So well, it looks like a singlet to me.
None.
Right, so it has 0 neighbors. Okay, so I want to point out the other things that confirm this. So notice that we have 2 protons here and 3 here. So our NMR needs to indicate a set of 2 and a set of 3, each of which do not have neighbors, or it needs to have 2 sets of 3 without neighbors. And what we're given is a set of 2 and a set of 3. So that confirms to us, why did those circles come with me? That's weird. Okay. That indicates set of 2, set of 3. So that further confirms this structure. So if we had had this structure, we would have had to have a methyl group that was a little further downfield with no neighbors, a methyl group a little less far downfield because it's not next to a carbonyl. They each would have integrated for 3. And then this particular setup on a benzene ring creates a very unique aromatic signal. So when they are directly across the ring from each other and it's di-substituted, the aromatic signal tends to be 2 doublets, and they would integrate for 4. So this NMR would have been very different from what we actually ended up with. So anytime you see like this and it integrates for 5, you know that there's only a single substitution on the benzene ring. So that's another way that you could have narrowed down your options pretty early, because that would have limited you to the 2 central ones. But anyway, there were a lot of different ways to narrow this down. But these types of questions that I asked is kind of what your thought process should be. You know, does my IR peak give me anything useful? How many different carbons should I be seeing? How many different protons am I seeing? Are there any like indicative peaks? Like, do I have aromatic protons? Do my alkyl protons have neighbors? Those are the types of questions that you want to ask in order to decide between possible spectra. And especially since in your exams, it's always going to be multiple choice. You're given the chance to kind of narrow down between several options. Okay, so we're actually out of time. I'll send out a key a little later today, and I'll send out some practice spectra.